So, in the last class we have seen this. We derived this impedance plane, and then based upon this we have derived a curve which is known as the lift off curve. And as I said, this will be the basis for eddy current testing. We also saw what will be the effect of sample conductivity on this lift off. So, if you have lift off curve like this, so this is air, and then if you use samples of different conductivity, like let us say you have bronze, then you have steel. In the order of increasing conductivity, you will get these data points, then aluminum and copper. Okay. So, if you join these points, you will get a curve like this. Okay. So, which is the conductivity curve. Okay. This also is so. So, as you increase the conductivity, you are drawing more and more energy out of the coil, and as a result the increase in the R will be more. So, this conductivity curve is obtained because for different materials the lift off curves will be like this. And if you join the endpoints of them, you get this conductivity curve, okay, as you could see. So, this is the effect of conductivity, that is also we saw. And one more thing probably I could tell you here, which is the effect of the frequency of the current which is used in the coil. And one more aspect about this effect of conductivity and combined with the frequency is that if you have a sample, let us say I have bronze, and if the frequency is 100 kilohertz, you will see the lift off curve like this. If you increase the frequency to 1 megahertz, you can see the same sample behaving like a more conductive sample. Okay. So, this is just to tell you that the frequency would also have some effect on the conductivity curve or the lift off curve. So, now let us see how this can be used to do eddy current testing. So, let us talk about the method of doing eddy current testing and see what kind of equipment and probe you need. So, let us first talk about the frequency which is used in the coil, because all you need in this case to do eddy current testing is a source of alternating current. That means, the probe that you have in eddy current testing is nothing but a coil which will carry this alternating current. Okay. And there is a particular frequency range in which this is used. So, we are talking about the testing method. So, in case of eddy current testing, the frequency varies between few kilohertz to around 5 megahertz. Okay. So, this is the frequency of the alternating current that is being used for eddy current testing. So, if you talk about the inspection system now, which is used for doing the test. So, as I said, The first requirement is what you need is a source of varying magnetic field, because that is what generates the induced current. And this is provided by a coil carrying alternating current. And the frequency of this current can be anything between 1 kilohertz to 10 megahertz, depending on the situation you could select from this frequency range. So, the probe that you have, as I would have told before also, primarily contains a coil which carries this AC current, and then of course, you need the sensor to detect any change in the impedance of the coil, as we have already discussed. So, this change will be generally very small. So, the detector should be able to detect this kind of minute changes. So, if there is a change in the coil in the impedance, so there will be a change in the current also, and as a result there will be a change in the magnetic field which can be detected by the sensor which is used. And of course, you need this electronic circuit to do that, okay, to detect that change and then give you a signal which can be seen on the screen, and based upon that signal you take a call whether there is a defect or not. So, you need this electronic circuitry to aid the interpretation. The magnetic field change. I would have said this before also, this technique and some of the other NDT technique, the indications are indirect, like what you have seen in case of dye penetrant testing and magnetic particle testing. The indications are direct, you see the defects visibly on the surface, but in this case the indications are indirect. So, they are subjected to interpretation in terms of a change in the magnetic field, and based upon that change this electronic circuit should give you a signal that you can see on the screen, and then that has to be interpreted in terms of a defect. So, this is all you have in the inspection system. You have a small probe which contains this coil which carry the AC current, and then you have a small box which will have all this electronic circuitry, and it will also have a small display, an oscilloscope kind of display, on which you can see the impedance plane, you can see the lift off curve, and if there is a crack or any other kind of defect, you can see that defect signal as well. Okay. So, this is a very handy system, a very small portable system. All you have is a small box which contains all this electronics, display and so on other things, and in that box you can, to that box you can hook your probe, you can connect the probe to that box, and you can connect it to a power supply, and there are systems also which can run on battery. Okay. So, this is a very handy portable system which can be carried anywhere, and you can do eddy current testing anywhere in the lab, outside the lab, or on site. Okay. So, now if you talk about the probes, there are different kinds of probes depending on what kind of sample you have and what exactly you want to inspect. Depending on that, you could choose one of these categories. So, let us talk about the eddy current probes. The first one that we have is known as absolute probe. This consists of only one coil, which will carry that current. Okay, so, it has two coils in the same housing, and when you move it on the sample surface, let us say there is a crack over here. When it is when the probe is on a defect free region, then there will be no signal between these two coils, or if both of the coils are on the defect, okay, then also there will be no differential signal between them, because both are at the same location and receiving similar kind of signal. But whenever there is like this, one coil over the defect and another coil is not directly over the defect like this, then a differential signal will be generated between these two coils. And this will be sensed by the sensors that you have in the system, and the crack signal will be shown on the display. Okay. So, this is based upon a differential signal between the coils when one of the coil will be over the defect. And the next one that we have is known as a reflection probe. So, like the differential probe, this also has two coils in the same housing, but in this case one coil is used to excite the current, and the other coil is used as a receiver. If there is a change, in order to sense that change, the other coil is used. So, that is used as a receiver. receiver to sense any change in the magnetic field. Okay, so this in terms of the construction of the coils, okay, these are the three categories, and in terms of the geometry of the coil, if you see, then also you have 3 or 4 categories of 3 or 4 different types of probes. One of them is surface probe. This is basically a pancake type flat probe, and as the name suggests, it is primarily used for flat surfaces. And large areas. But you might have other kind of areas also to be inspected. For example, you might have a bolt hole and you want to inspect these threads which are inside this bolt hole. So, in those cases you need to insert the probe inside the hole. So, you have this bolt hole type or pencil type probes which can be inserted inside a hole to inspect the inner diameter. So, this will be construction wise, this is a coil mounted inside a cylindrical housing. Okay. And the diameter of this cylinder can be varied or can be chosen based upon the diameter of the part. So, it should be little less than the diameter of the part, so that it can go inside, and at the same time it should not be very different also. It should not be too low compared to the diameter of the part. So, it should be closely fitting inside the bolt hole, so that you would be able to inspect the circumference of the part. Okay. So, it may be the probe might just look like this pen. Okay. If you have a look at this pen, many time eddy current probes have this kind of geometry and this kind of appearance. Okay. So, you can take this, and if you have a hole like this, you can put it inside the hole diameter, the inner diameter, and you can inspect the circumference. So, these are the bolt hole type probes. Then if you want to inspect the outer diameter of any part, so then you need to have an encircling kind of probe which can encircle the part and induce the current along the outer periphery or the outer diameter of the part, so that you would be able to inspect the circumference along the outer dia. So, this probe will encircle the part, right. Like this. So, this will this is the probe, and in this case this will have a hole like this, and through this hole you have to insert the part to be inspected in this manner. Okay. So, this is the sample, and the coils are around this hole. So, as you insert this through this hole, the current will be induced on the outer diameter of the sample, and you will be able to inspect the outer dia and the circumference. Similarly, you have ID or inner diameter probe. So, this is OD probe, and similarly you could have ID probe for inspecting the inner diameter, and sometimes these ID probes are also known as bobbin probe. So, this is a feed through probe like what we discussed for the bolt hole kind of probes. So, this has to be feed through the sample hole. So, you have to insert it inside the inner diameter to inspect the inside diameter. So, this is inserted into hollow parts. Such as pipes, and similar hollow products to inspect the inner surface and the inner diameter. Okay. So, depending on the geometry, these are the different types of probes that you have. And finally, we will see one more aspect about this inspection system as to what kind of circuit is used to get a sense of this change due to the presence of a defect. So, as I said, if there is a defect, there will be change in the eddy current, and as a result of that there will be a change in the magnetic field of the coil, which has to be sensed by the detector and generate a signal which can be shown on the display. Okay. So, this is one example of a circuit which is used to detect this change, and this is known as a balance bridge circuit. So, what you have in this case, it is like this. You have the primary coil or the probe here, and then on the other side there is a reference coil, like this. This is the probe. So, your sample will be close to this. And then the detector to detect any change will be connected to this. Okay. So, if there is no defect on the sample when you bring it close to this probe, to this primary coil, then there will be no difference between this reference coil and this probe. So, there will be no signal in this detector. Okay. On the other hand, if there is any defect on the sample, then there will be a change in this coil, in this probe, as we have seen before, and due to that change, now since the reference coil is kept constant, so there will be a differential signal between the reference coil and this probe due to that change, and as a result of that this detector will sense a change. So, it will pick up a signal, and that is what is going to be used finally for the eddy current system to make indications about the flaws. So, this is one of the examples, one of the circuits which is known as balance bridge is used, but there could be other type of circuits also which can also be used to detect this change. Okay. So, this is about the inspection system. So, we have learned about the basic principles, we have learned about the inspection system also, and now in the next class we will see the other things as to how exactly it is used, what are the different applications, and few more aspects about eddy current testing. So, for today this is all I have. Thank you.